Okay, guys, I'm back with the second page of your 7.3 day 2 notes. All right, so these equations now that we're going to solve are, you're going to have to use a trigonometric identity. So if you think about when we solve equations, we normally don't want to solve an equation with more than one variable in it. Like if you can think of a system, if it had an x and a y in it, then we kind of had to pair two equations together to be able to solve for x and y. So a lot of times when you're solving trig equations, you don't want more than one trig function involved in the equation. You either want it to be all cosines or all sines or all tangents or whatnot. So if you start coming across equations that have different trig functions in them, you might have to take one of the trig functions out and replace it with an equivalent statement using a trig identity. And that's how you might be able to get this all in terms of cosine or all in terms of sine. And that way we're not working with two different trig functions, okay? All right, so what I've done is I've listed the Pythagorean identity that came from x squared plus y squared equals 1. But since x equaled cosine and y equaled sine, we were able to use this as our first Pythagorean identity. And then just by manipulating him, we were able to create more trigonometric identities, okay? All right, so look what it says. Solve each equation on the interval 0 to 2 pi. So again, you're only allowed to say angles between 0 and 2 pi are answers to this equation. We can include 0, but we cannot include 2 pi. All right, so look at this one. 3 cosine theta plus 3 equals 2 sine squared theta. So you might be thinking like, oh, it's sine squared, it's going to be a factoring problem. It may be. The problem is I'm not going to be able to factor this when it's in terms of cosine and sine squared theta. So since our Pythagorean identities are actually focused on squared sines and cosines and squared tangents and secants and cotangents and whatnot, you're probably more likely than not going to have to take the sine squared function out and replace it with an equivalent statement in terms of the non-squared function, okay? So again, if I tried to take cosine theta out and put sine theta in his place, well, cosine theta, none of these functions have just a cosine theta in them. So it's not like I could go look for an equivalent statement. However, if I wanted to take sine squared theta out and put more cosines in his place, I might be able to find what sine squared theta is equal to in terms of a cosine function, all right? So it's most likely going to be the squared one that you look to remove because he's going to be the one that most likely has an identity involved. So guys, think about it. How could I get sine squared theta out and more cosine thetas in? Well, guys, look right here. It says sine squared theta is equal to 1 minus cosine squared theta. So I could take sine squared theta out and put 1 minus cosine squared theta in. And then this equation would only have a cosine function in it. So that's what we're going to do. We're going to take sine squared theta out and we're going to put what he's equal to in terms of cosine in. So that's going to be 3 cosine theta plus 3 equals 2 times, not sine squared theta. Who does sine squared theta equal? 1 minus cosine squared theta. All right, I'm going to distribute my 2 and we're going to be good to go. So now I'm going to have 3 cosine theta plus 3 equals 2 minus 2 cosine squared theta. So it's a cosine squared one, right? So it might involve factoring. So let's get all of our equation on one side set equal to 0. Well, since the number in front of the squared one is negative, I'm going to add this to that side and minus it over so that my coefficient to the squared term is positive. Just like when I go to factor, I like the number in front of the squared piece to be positive. So I'm going to add him over, which will mean it'll lead with a 2 cosine squared theta. Then I'll have my plus 3 cosine theta. And then when I minus 2 to the other side, 3 minus 2 will be a plus 1. Equals 0. And then again, if you feel better or more confident putting a u in the place of cosine theta, so then it will be 2u squared plus 3u plus 1, please have at it. I'd like to see you guys get good at factoring this just the way it is. So let's try to factor this. All right, so what times what will multiply to 2 cosine squared theta, a 2 cosine theta, and a 1 cosine theta, just like a 2u and a 1u. would have done the job for 2u squared. All right, and then whatever I put here and here has to multiply to 1, and then my rainbows better add up to 3 cosine thetas. So the only thing that multiplies to 1 is 1 and 1, and then if I put both as plus plus, it'll multiply to a positive 1. This will be 1 cosine theta plus 2 cosine theta. I'll get my 3 cosine theta. All right, once we factor it, we set each factor equal to 0. So what's going to take or make 2 cosine theta plus 1 to equal 0? Or what's going to make cosine theta plus 1 equal 0? Okay, solve this for cosine theta, minus 1, divide by 2, and you are left with the statement cosine theta equals negative 1/2. All right, let's work the quadrants, right? According to all students take calculus, the cosine of an angle would have given you a negative ratio for an angle in quadrant 2 and an angle in quadrant 3. Okay, does anybody remember the cosine of what special angle? 30, 45, or 60 gave you a ratio of 1/2. Well, remember the sine of a 30 is 1/2, so that means the cosine of a 60 has to be 1/2. So it's a 60, it's a pi over 3 and a pi over 3. So what multiple of pi over 3 lands in each one of these quadrants? Well, again, if that's pi, that's 3 pi over 3. So that makes the one before it 2 pi's over 3, and the one after it 4 pi over 3. So the two angles that make this a little equation true are 2 pi over 3 and 4 pi over 3. Okay? All right, hang on to them. And now what angle makes this little equation true? So solve for cosine theta, and you're left with cosine theta equals negative 1/2. Well, the cosine of what angle is negative 1? That you should know is one of your quadrantals. That's a 0, a pi over 2, a pi, a 3 pi over 2, or a 2 pi. So if you picture your unit circle, you have 1, 0, 0, 1, negative 1, 0, and 0, negative 1. So the cosine of what angle had a ratio of negative 1? Well, whose x-coordinate was negative 1? Pi. So theta would have had to be pi radians to make that little equation true. So that means you end up with 3 answers. 1, 2, 3 angles that will make this equation true. Okay? All right, let's come over to this one. If we have to solve this one, cosine squared theta minus sine squared theta plus sine theta equals 1. So I have a cosine squared theta, I have a sine squared theta, and I have a sine theta. So I have 2 terms in terms of sine, and then I have a cosine squared. So again, normally you're looking to remove one of the squared functions because all of your identities based off of a sine function, right? So a sine squared or a cosine squared or a cotangent squared. So normally you won't be able to replace a sine theta with anything because sine theta is not involved in any of these functions, all right? But because we have a sine theta that I shouldn't be able to remove, that means you want to leave it in terms of sine and get the cosine squared out. So how can I get cosine squared theta out and more sine functions in? Well, if you come up here, according to this, cosine squared theta is equal to 1 minus sine squared theta. So I can take this out and put what he's equal to in his place. So that's what we're going to do. We're going to take cosine squared theta out and put what he's equal to in terms of sine in. So instead of cosine squared theta, I'm going to use 1 minus sine squared theta. And then minus sine squared theta plus sine theta equals 1. Okay. Well, now I have 2 of these. So if I add them together, I have negative 2 sine squared thetas. So negative 2 sine squared theta, and then plus sine theta, and then plus the one that's still on this side equals 1. Well, again, if I'm going to use factoring, I want to get everything on one side set equal to 0. So could I minus the 1? Yes, and then I could always factor out a negative or whatever. And because I have to move everything anyway, I'm just going to actually add this over minus him and minus him to get it equal to 0. All right, so if I add that over, that's going to become 2 sine squared theta minus sine theta. And then when I minus 1 to the other side, they actually cancel out and it's equal to 0. Okay? All right, so now you should be thinking factoring, but also what does a sine squared theta and a sine theta have in common? A sine theta. Factor it out. So if you factor out a sine theta, that's going to leave you with 2 sine theta minus 1 equals 0. And then after you factor, you set each factor equal to 0. So what's it going to take to make sine theta equal 0? Or what's it going to take to make 2 sine theta minus 1 equals 0. Okay? All right, let's solve this one first. The sine of what angle equals 0 as a ratio? Well, again, if your sine function has a ratio of 0, that's a quadrantal. That's a 0, a 90, a 180, a 270, a 360, whatnot. So if you think of your unit circle, I have the point 1, 0, 0, 1, negative 1, 0, and 0, negative 1 at my quadrantal angles, right? Okay, the sine of an angle was represented by his y-coordinate. So who has a y-coordinate of 0? Well, 0 does. So theta could have been 0 radians. Pi does, so it could have been pi radians. And so does 2 pi. But if you remember, we're not allowed to include 2 pi. So I really can't include him. So right now, it's just 0 and pi that make that little equation true. Okay, come over here. Now we solve this one. Add 1, divide by 2. Sine theta has to equal 1/2. So the sine of what angle would have been 1/2? Well, let's work the quadrants, right? If you have the sine of an angle equals a positive ratio, then that would have been an angle in quadrant 1 or 2. All students, right? Okay, so now the sine of what special angle would have been 1/2? 30, 60, 45. It's a 30. It's a pi over 6. So now what multiple of pi over 6 do you have in each quadrant? Well, pi over 6 in quadrant 1 is pi over 6. If this is pi, that's 6 pi over 6, which means the one before it is 5 pi's over 6. So theta could have been pi over 6 or 5 pi over 6 and made this equation true, which leaves you with 1, 2, 3, 4 answers to that equation. Okay? All right, let's try this one. Cosecant squared theta equals cotangent theta plus 1. See, that's a problem. You have an equation that has more than one trig function in it. This one is not squared. So usually the one that is not squared is the trig function you have to leave, and it is the squared one that you should be looking to get out. So is there anything you can find in your identities where cosine squared theta could come out of the problem and we could get more cotangents in? Well, guys, if you go up to your identities, cosecant squared theta is here and here. And if you notice, cosecant squared theta is literally equal to cotangent squared theta plus 1. So I'm going to be able to put this in for cosecant squared theta. So we're going to take cosecant squared theta out, and we're going to put who he's equal to, cotangent squared theta plus 1 in. So cotangent squared theta plus 1 equals cotangent theta minus 1. All right, well, it is a squared function, so let's try and get everything on one side set equal to 0. So I like that the number in front of him is positive. I'm going to move everything this way, right? Oh, sorry, I'm looking at it and something felt wrong. This is a plus 1, this should have been a plus 1, sorry. Okay, so now let's minus cotangent theta. So now I'm gonna have cotangent squared theta stays. I'm gonna minus my cotangent theta over, and then when I minus 1 over, they'll cancel, and now it's just equal to 0, and the other one is gone. All right, so now if I try to factor this, what does a cotangent squared theta and a cotangent theta have in common? A cotangent theta. Factor 1 out. So if I factor out a cotangent theta, that'll leave me with cotangent theta minus 1 equals 0. All right, now we factored it, set each factor equal to 0. I'm just going to do this one. Cotangent theta equals 0. And then cotangent theta minus 1 equals 0. All right, let's do this one first. Well, again, I don't really want to work in terms of cotangent. I'm going to work in terms of his reciprocal, tangent. So the cotangent of an angle equals 0, then the tangent of that exact same angle would have been his reciprocal. So if you think of this as 0 over 1, his reciprocal is 1 over 0. That's an undefined ratio. So you are looking for angles between 0 and 2 pi who had an undefined ratio as per the tangent function. So if you think of your quadrantals, because it would have to be a quadrantal, none of your 30s, 60s, or 45 had an undefined tangent ratio. All right, we have 1, 0, 0, 1, negative 1, 0, and 0, negative 1. The tangent, by definition, was sine over cosine, or y over x. So what angles, when you put y over x, do you get an undefined ratio? Well, 0 over 1 is not undefined. 1 over 0 is undefined, so that's pi over 2. Theta would had to have been pi over 2. All right, 0 over negative 1 is not undefined. Negative 1 over 0 is undefined, so that's 3 pi over 2. 3 pi over 2 would have an undefined tangent ratio. All right, so those are the, and then 2 pi would not, it'd be 0 over 1. So those are the two angles that are gonna make this part of the equation true. All right, come over here, add 1. The cotangent of theta has to equal 1. Well, again, I'd rather work in terms of the tangent function. So if the cotangent of this angle had a cotangent ratio of 1, then the tangent of this angle would have the reciprocal of that ratio, which is also 1. All right, let's do this. So the tangent of an angle gets you a positive ratio of 1. Well, according to All Students Take Calculus, the tangent of an angle gets you a positive ratio for an angle in quadrant 1 and an angle in quadrant 3. Now, what special angle had a tangent ratio of 1? A 30, a 45, or a 60? It's a 45. So that's a pi over 4. So you have a multiple of pi over 4 in quadrant 1 that makes this true, and you have a multiple of pi over 4 in quadrant 3 that makes this true. Well, pi over 4 in quadrant 1 is pi over 4. What multiple of pi over 4 lands in quadrant 3? Well, if this is pi, that's 4 pi's over 4. So the one right after it is the fifth pi over 4, or 5 pi over 4. So in order to make this equation true, theta could have been pi over 4 or 5 pi over 4. And you end up with 4 answers. 1, 2, 3, 4 answers to this trig equation. Okay? All right, perfect. So that's how we work with identities and taking one trig function out and putting another trig function in its place. Because again, you want these equations to only have one trig function. You don't want sine and cosine. You don't want cosecant and cotangent, right? So like I said, a lot of times, if you can get the squared one out and then another one of this type of function in, that's your best bet. Okay, the other two that I want to go over is, well, they're not all going to be special ratios. Like we have 1/2 and root 3 over 2 and zeros and ones and whatnot. If it's not a special ratio, then it's not a special angle. And you're going to have to use your calculator for those ones. So I just kind of wanted to go over a couple that you could use a calculator on. All right? Or that you'd have to use a calculator on. All right, solve each trig equation on the interval 0 to 2 pi. So again, you're still only looking for angles between 0 and 2 pi who make these equations true. All right, so this one says the tangent of angle theta has to equal -2. So normally you'd have to get tangent theta by itself, but it already is, and now it has to equal a ratio of -2. Well, -2 is not a special ratio for a 30, 45, or 60, or a quadrantal angle as per the tangent function. So that just means you're not going to be able to do this by hand. This is just some random angle. It's not some special 30 or 45 or 60 or whatnot. So you'd have to do this. If tangent theta is by himself, the only way to undo it is take the inverse tangent. So you're going to have to inverse tangent both sides. Okay, the inverse tangent will undo the tangent function and leave you with theta equals whatever angle the inverse tangent of -2 tells us. But here's the problem. We know the inverse tangent, right? The inverse tangent is only capable of spitting out angles in quadrant 1 or quadrant 4, right? Angles between pi over 2 and -pi over 2. We already know if you take the inverse tangent of a negative ratio, it's going to spit out an angle in quadrant 4 between 0 and -pi over 2. So the calculator is going to give you right now some angle between 0 and -pi over 2, which is -1.57-ish, okay? But any angle between 0 and -1.57 isn't on this interval. Any angle between 0 and -pi over 2 is not on this interval. So the answer the calculator is about to give you is not even an angle that you're going to be allowed to use. But you need that angle to get started. So you still have to do it. So ask your calculator. Make sure you're in radian mode. All right. Go to mode and make sure you are in radians because they want it in radians. Okay. All right. And now ask your calculator what is the inverse tangent of -2. And then watch, it's going to give you some number between 0 and -1.57. Okay, -1.1071. I'm going to keep 4 decimal places. So right now it says -1 1.1071 is an answer. And it is. It is an angle that will make this equation true. It's just not on the interval of angles that we are allowed to say are answers. Okay, so what you're going to use him for is to get your reference angle. So if this is the angle right here, right, that's the angle from 0 to negative 1.1071. What is the reference angle then? The reference angle, well, if you think about it, the reference angle of negative pi over 6 was pi over 6. So the reference angle is the positive version of this. So your reference angle is going to be positive 1.1071. Just hang on to that, okay? Okay, so now we already know that the angles between 0 and 2 pi that make this true, right? According to All Students Take Calculus, if the tangent of an angle got you a negative ratio, then you must have been taking the tangent of an angle in quadrant 2 or quadrant 4, right? Because those would have been All Students Take Calculus. Those are the two quadrants where the tangent gets you a negative ratio in, like a negative 2. So there is an angle in quadrant 2 that has a reference of 1.1071 that makes this true. And there is an angle in quadrant 4 with a reference of 1.1071 that makes this equation true. So what is the real actual measurement of this angle and this angle? Okay, well, here we go. Well, guys, we have to figure out if I went from here to here, what real angle is that, right? Well, don't you agree? All the way to here is pi radians. So this angle right here is pi minus that reference angle. That's how big he would have been. So the answer is the quadrant 2 angle is going to be whatever pi minus that reference angle is, because you're this many radians short of pi radians. All right, so the first answer is going to be whatever pi minus 1.1071 is. Let's ask our calculator. Second pi minus 1.1071. Hit enter, and it's about 2.0345 radians. I don't know how many decimals your homework will tell you to keep. About 2.0345 radians is one answer. That's your quadrant 2. If you are an angle in quadrant 2, then you are between pi over 2, which is 1.57, and pi, which is 3.14. And isn't 2.03 in between 1.57 and 3.14? Yes. So that is definitely a quadrant 2 angle that'll make this equation true. All right. Again, because I've rounded, I don't know if I'll get the exact answer, but if I take the tangent of this angle, what is the tangent of 2.0345 radians? It should be close to negative 2. Whether it's going to be like negative 1.999 or something, we'll see. Yeah. So it's very, very close. Because I rounded, it can't make it entirely true. But I have to round, okay? All right. Now, this answer, what angle in quadrant 4 makes this true? Well, the angle in quadrant 4 is going to be, well, if you think about it, what angle did I rotate to all the way around to that one right there? So that is actually, if I kept rotating, this is where 2 pi radians would have been. But I am short by a reference of 1.1071. So whatever 2 pi minus my reference 1.071 is, that's going to be the angle that landed in quadrant 4. So ask your calculator, what is 2 pi minus 1.1071, hit enter, and it's about 5.1761 radians. 5.1761 radians. All right, and that's the quadrant 4 angle that would have made that equation true. All right, and again, I can test it. If I asked my calculator what is the tangent of 5.1761, again, I rounded, it should be close to a ratio of negative 2, and it is, okay? All right, cool. All right, before I do the last one, I just want to do one more of those. So let me just give you another example. What if you had to solve the, let's call this 4C, but I'm going to do it before 4B. What if they asked you to solve for theta in between 0 and 2 pi? If it said secant theta equals negative 2.7, right? Okay, well, your first goal would be to get secant theta by itself, and it is. You're good there. All right. Well, I don't want to work in terms of secant, so I'm going to work in terms of cosine. So if you think of this as 1, if the secant of this angle equals that ratio, then the cosine of the exact same angle would have the reciprocal ratio. And I'm literally just going to flip that over. It would be negative 1 over 2.7. All right, no, we're not supposed to have decimals inside of fractions, but it's fine. We're going to use the calculator anyway. So the cosine of what angle gets you this ratio? This is clearly not a special ratio. This is not 1/2. This is not root 3 over 2 or root 2 over 2. It's not special. So we're literally going to have to use the inverse cosine. So let me just kind of set you. Ooh, whoa, sorry, I hit the camera. Let me just set you guys up. You're going to have to inverse cosine both sides to solve this, okay? The inverse cosine is only capable of spitting out angles between 0 and pi, quadrant 1 and quadrant 2 angles. We already know that if you took the inverse cosine of a negative ratio, it spits out an angle in quadrant 2. So the calculator is about to get us the quadrant 2 angle. Okay, now we can also break this down. The cosine of an angle would have equaled a negative ratio for angles in what 2 quadrants, right? All students take calculus. The cosine of an angle equals a negative ratio. All calculus is where it's positive. That means there is a quadrant 2 angle and a quadrant 3 angle that are going to make this true. The inverse cosine is about to get us the quadrant 2 answer. All right, so inverse cosine, negative 1 divided by 2.7. And it is about 1.9502. All right, so theta equals 1.9502. It got us that answer right there. Okay, but so right now, that's one of your answers. The problem is, in order to find out the angle in quadrant 3 that also makes this true, I need the reference angle so that I can use the reference angle in quadrant 3. So if this is 1.9502 radians, well then what is the reference angle right here? Well, this is pi, right? So the reference angle, is whatever pi minus that angle is. Pi minus 1.9502. Well, what is pi? Ask your calculator. What is pi minus 1.9502? And it is 1.1914. So that's your reference angle. So now to find quadrant 3's answer, it also has to have a reference of 1.1914. So to find out your quadrant 3 angle, theta has to be, well, it's going to be, there's pi, and you have to go 1.9114 radians past it. So what's pi plus your reference angle, 1.1914? And theta will equal, well, what's pi plus 1.1914? And it's 4.33, I'm going to go 30, okay? 4.33, and then 29, that would go up to, I'm going to say 30. All right, so the two angles, the quadrant 2 and quadrant 3 angle that makes this equation true is 1.9502 radians and 4.3330 radians are your two answers, okay? All right, perfect. Okay. So again, those can be a little tricky because you have to be able to find your reference angle with these decimal versions of these angles, okay? All right, remember, it's usually just pi minus the reference, pi plus the reference, or 2 pi minus the reference, okay? All right, last one. The last one is actually a graphing calculator question. It says use a graphing calculator. This one's hard to solve because even if you tried to get sine x by itself, you're only taking the sine x. You have another x on the outside of this function. So what they're going to ask you to do is treat the left side and the right side separate. when does the left side of the equation equal the right side of the equation, right? So you're going to go to a graphing calculator and let y1 equal the left side. 5 sine x plus x. And then you're going to let y2 equal the right side of the equation, 3. And then you're going to use that intersect feature. Where do these graphs intersect? All right, let me just give you a little bit of some programming. You're probably going to have to mess with the window in order to see the graph, right? You're dealing with the sine function, which has a period of 0 to 2 pi, and it has an amplitude of 1. But if you notice, this sine is definitely being times by 5. So that's definitely making the y values 5 times as big. All right, if I minus this over, it could have been shifted or whatnot. So I'm just going to mess with my window. As far as my x min goes, right? X's are my inputs, my angles. Well, I know it goes from 0 to 2 pi, so I want to get a couple periods going. So I'm going to go, my x min is negative 2 pi, and you can literally put in negative 2 pi. It'll just change it to a decimal for you. I want my x max. I'm going to try and see at least 2 periods, so I'm going to do 4 pi. All right, and then my scale, well, guys, let's count by pi's over 2, right? Like 90 degrees, like we normally do by the quadrants. I'm going to put pi over 2 as my scale. And then as far as the y's are concerned, like I said, this is going to be 5 times 1 at least. So let's go to like 10 and negative 10. So my y min, let's go to negative 10. And my y max, let's go to positive 10. And then we'll just use the scale as 1. Okay? All right, so let's do that. So if you go to y1, I already did it. You're going to put 5 sine of just x, that's all you're taking, and then this x is on the outside, plus x, and then let y2 equal 3. And then make sure none of your plots are on for stats or anything. You don't want any of your plots on. All right, and then you can just literally hit enter, enter, and then ask it to graph them. Oh, let's go to our window. Let me get mine back to normal, so I'll do it with you. A little zoom. Give me 1 second. Okay, so here's my window, right? Let's make our x min negative 2 pi, and watch, you'll change it to a decimal the minute you hit enter. All right, that's negative 6.28, right? Negative 2 times 3.14. Let's make our x max 4 pi. Let's see 2 periods at least. That's going to change it to a decimal. All right, and let's make our scale pi over 2. Let's count by pi's over 2, like a normal graph we do. Okay, it's going to change it to a decimal, 1.57. All right, x min, I'm going to go with negative 10. I'm going to keep it at 10. I'm going to keep a scale as 1. So now hit graph. Okay, so this is y1. This is the sine curve, the sine x plus x, right? The 5 sine x plus x. And then this is the line y equals 3, our second equation. So I can see that they intersect 1, 2, 3 times. That means there are 3 angles that are going to make this equation true. So in order to find out, well, what x values, what angles do they intersect at, I'm going to use that intersect feature. So above trace, you have that list of calculations. So hit second, trace, and we're going to ask it to intersect. Where do these graphs intersect? So hit 5, right? And then that little cursor, I'm going to try and find the first one first. Doesn't matter. So I'm going to use my left arrow to move that cursor to where they first intersect. All right, so that cursor it's on the sine curve right now. Hit enter. Then it jumps to the second curve, the straight line. And as long as it's close to that intersection point, you're good. So just hit enter. And then guess yes. They intersect approximately when x equals 0.5192. All right, so that's one angle that should make this equation true. All right, now let's get, where do they intersect at what x value? Right there. All right, so they'll go to that second trace button again. Let's ask it to intersect, number 5. And now move your right arrow. Let's get closer to that second intersection point. All right, that's good. Hit enter. It jumps to the line. It's pretty close to the intersection point, so just hit enter. Guess yes. And it intersects when x is approximately 3.17770. All right, so that's an answer. And then the last one, it intersects for a third and final time right there. Let's go get that x value. So go to second trace. number 5 intersect. And now use that right arrow. Let's move it closer to this second intersection point. All right, that's pretty good. Hit enter. Now it jumps to the line. It's close. Hit enter and guess. And when X is about 5.7103. All right, and those are the 3 X values or the 3, oh, my camera's not focusing. Those are the 3 X values or angles that'll make this equation true. Okay, all right, guys, I know that's a lot, but reach out to me with any questions that you may have, and good luck.